Today we look at section 10.2, which uses chi-square and talks about goodness of fit. So the goodness of fit of a statistical model describes how well the model fits a set of observations. It's kind of a weird phrase, this goodness of fit, but we're basically seeing how well data fit into a known pattern or a distribution or something like that. So the example I've got here is from M&M Mars. And a while ago they had this distribution claim on their website that showed the color. I guess it's been quite a few years now, but they had the color of the M&M, and this is for plain M&Ms, and then the distribution of these colors. So what we do sometimes is in class, when we have enough time, we have a final quiz where I hand out bags of M&Ms, and the students open up the bags and see. We count each sample of M&Ms. Each bag of M&Ms is a sample, and we look at each sample and see if it seems to match this distribution. So it's unlikely that any sample would match this exactly, right? So we want to see, does it match close enough so that it looks like the M&Ms came from this sample? So this is an example of this. So we could gather a random sample of these M&Ms and use this what's called the goodness of fit test to see whether our sample distribution differed significantly from this distribution here claimed by the company. In this section, we use the goodness of fit test to investigate how well a sample distribution fits a given distribution. And we will see that this can also be used to determine whether a distribution is normal. And this would be a really important point right here. So if you have a sample of data and you want to know whether or not they follow a normal distribution, that could be an important question, because if the data that you have comes from a normal distribution, then there are all kinds of statistical analysis that you can use, because the normal distribution is well understood. So it would be important if you could figure that out, because like I said, if it did follow a normal distribution, there's a lot of options you can use to study the data. So there's a famous example from history here. So I'm going a ways back, and everybody's probably heard of Gregor Mendel, pretty much the founder of the theory of genetics. And he published a famous paper outlining the results of a series of experiments with peas, and you probably even heard about that example. This was an extremely important paper, and his theory of genetics has become a cornerstone of basic science. And it was that paper he published about the pea plants and the distribution of colors. So it turns out that genes determine the color of the seeds, whether they're going to be green or yellow, but we didn't really know what genes were yet. So he was one of the people who was figuring all of this stuff out. So in 1936, R.A. Fisher, who we've mentioned in class a couple of times, this guy is like Michael Jordan of statistics. So he pretty much had a hand in everything that we study in our class. R.A. Fisher was all over it, and was a giant during this early period of statistics. So he published a paper that analyzed Mendel's data and concluded that they fit his theory too well, way too well, in fact, to be explained by chance alone. So using the chi-square goodness of fit test, he showed that the probability that an overall data fit was at least as good as the one reported by Mendel would have occurred with this probability. In other words, this is the p-value. We've never seen any kind of p-value even close to that small. So as an example of this, I'm going to mention something we've mentioned before, but this is a really easy variation of or version of it. So let's say you wanted to buy a 6-sided die, and you are like an avid D&D player, and you want to make sure this is a fair die. So you go down to the store where they sell all kinds of dice, and you're like, hey, I need a 6-sided die. I need it to be really fair. And the person behind the counter is like, you know what? I got just the one for you. On your way down here, I rolled this 6-sided die 300 times, and this is what happened. I got 51s, 52s, 53s, and so forth. Now, most likely, you would look at that person with a little skepticism, right? Because it is extremely unlikely that this would happen. It's just, there's variation and randomness built in so that even if it's a fair die, you wouldn't expect this to happen. So even if you change it a little, like let's say I'm just going to change a few of these. So let's say this was 48 and then 51 and 51. That's still a little too perfect. Well, that's a little bit what was happening up here. So Mendel looked at the research paper and he's like, Fisher looked at Mendel's research paper and it's just like, there's just no way. There's just no way this would ever happen this way. And it wasn't that he disagreed with the theory at all, but this caused a tremendous amount of stress in the science world because it's like two giants in their fields, but there really shouldn't have been stress. And Fisher said that he, was not questioning the science or anything like that, but he believes that the data were probably manipulated by assistants or an assistant who knew the results that Mendel expected. Because you have to remember, Mendel was a powerhouse in the field, and if you are a student maybe working for him, and you know what the theory says should be, what should be happening with these green and yellow peas, well, you might be likely to discard a plant that doesn't agree with the theory because, maybe you think, well, maybe I didn't water that one correctly, or, I really didn't, this one wasn't in the sunlight enough, I'm not going to count that one. And it's just kind of easy to throw out some of the data so that things fit exactly according to theory. So that's sort of what was happening there. So it caused a bunch of stress, but the science is sound, and the test that R.A. Fisher used is what we're going to use also. But in the one of the takeaways is that science is messy and probabilistic. It's not so exact. There's always going to be unexpected things. There's always going to be randomness and variation and all of that messiness built into science. So what we'll do to look at this is look at this example on page 649, number 16. And this one has to do with the fair dice. So this one says, a gambler complained about the dice. They seemed to be loaded. The dice were taken off the table and tested one at a time. One die was rolled 300 times and the following frequencies were recorded. So right here is what they're talking about. So this one die was taken, rolled 300 times, and these are the frequencies that were recorded. And then before we get there, let's just take a look at this. So fair dice have a uniform probability distribution. So uniform distributions, I had just mentioned once or twice. We don't study them much. They're kind of boring. So sometimes they're called rectangular distributions. And the reason they're kind of boring is because it's like this one here. If you have a fair, let's say you have a fair 6-sided die, well, the probability that you get a 1 is 1 out of 6. Probability you get a 2, 1 out of 6. 3, 1 out of 6. All the way down the line, they're all the same. And that's why you get the name of uniform. So all the way down we go. And the probability is 1 out of 6 everywhere. So that means that if in a perfect world with no variations, no randomness, our expected value here would be 50 all the way across out of 300 rolls, right? And this is what this die had. So again, in reality, we wouldn't expect there to be exactly 50 of these and 50 of these. Just like if you flip a coin 100 times, nobody's going to be shocked if you don't get 50 heads and 50 tails out of 100 coin flips, right? So this is like that. Basically the question we have to come up with is, are these numbers close enough to 50 to where we think, yeah, this is probably a fair die, or are they not close enough? That's the question we have to consider. So what we would do is we will find the expected frequencies, and compare them to the observed frequencies. And again, these are the observed frequencies here. And we talked about what the expected frequencies are. We'll talk about it a little bit more detail in a second here. So calculating expected frequencies. So we're always going to have to calculate these expected frequencies for a goodness of fit test. An expected frequency, there's a little formula for it. It is going to be the probability assigned to a category whatever that is, times the sample size n. And you don't really need this formula. It's very intuitive what you do here, but there's the formula for you. So looking at this problem continued, there's this, a series of steps they want us to walk through. And the problems, each of these problems has directions over on page 645 at the bottom of the page and then the top of page 646. And it's a hypothesis test, so it's similar to what we've done throughout chapter 8 and also in 10.1. So it says state the level of significance, null, and alternate hypothesis. So the null hypothesis and the alternate hypothesis. So the level of significance they tell us on this one, they tell us it is 0.01. And now we have the null and the alternate hypotheses. So if you guys remember from 10.1, we were testing independence, and the null and the alternate hypothesis could pretty much be, or the very same format for all of them. In 10.1, when we tested independence, we assumed that the two things we were considering were independent, right? We assume the two variables are independent, and the alternate hypothesis would be that those two variables were not independent. Oh, we have something similar here. So when we're testing the goodness of fit, we're going to test two distributions. We're basically seeing if they're the same. We're going to see, do these distributions, does one distribution fit this other distribution? So for this particular problem, we're going to see, does the distribution of outcomes for this six-sided die that we have, does that distribution fit the perfect distribution of 50 for each of those? We're going to see if they're the same distribution. So the null hypothesis is always going to be the two distributions are the same. So if you remember in 10.1, we assumed the two variables are independent. In 10.2, when we're going to do the goodness of fit test, we assume the two distributions are the same. So in this problem, that means the die is fair. I'm just going to put this, really we want to know if the die is fair. And if the two distributions are the same, the die will be fair. And then the alternate hypothesis, of course, is going to be the two distributions are not the same. So if the distribution of outcomes from this particular six-sided die does not match the expected distributions, which would be 50 all the way across, that means the die is not fair. And remember, when we say matches the distribution, it doesn't mean we expect to get 50s all the way across. We just expect to be kind of close. And we measure that kind of close using statistics. So in 10.2, you're pretty much, this is going to look very similar every time. We're going to assume the two distributions are the same, and the alternate hypothesis would be the two distributions are not the same. And then there'll be something that means in the context of the problem. But basically, these are going to all look very similar to this. And then the note is we will use your new favorite distribution, the chi-square distribution, for goodness of fit tests. So we are going to compute the sample test statistic. Now, if you guys remember 10.1, that was a nightmare to do by hand. Well, this one in 10.2, it's really the same formula, but it's much easier to do here. So what we have to do is figure out the expected frequencies. Now, here's where this particular problem is a little weird compared to most, because most of the time these outcomes are not going to have the same expected frequency. They're only going to have the same here because it's a six-sided fair die. So the distribution of outcomes for each of these sides is the same. So let's say you didn't know much about a six-sided die and you wanted to figure out the expected frequency of this, of getting one. So you've got a six-sided die, and you want to figure out, if I roll this 300 times, how many ones would I expect to get? Well, you'd say, well, what is the probability of getting a 1? Well, it's going to be 1 out of 6, right? That's probably that outcome. And then, well, how many times am I going to roll this? I'm going to roll it 300 times. So to figure out this number right here, it's just going to be 1/6 times 300. And that is using that formula above. If you look for the formula above for expected frequency, it says probability assigned to the category, 1/6, sample size 300. So right here we are going to get a 50. And as you can imagine, every other side is exactly the same. That's what's unusual about this problem. So listen to this. This is an important point. When you calculate these expected frequencies, they are usually all different. The only reason they're the same here is because we have this weird case where for a six-sided die, we have a uniform distribution. Okay, so everybody's good with that, right? Normally, these outcomes will not have the same expected frequency, and you'll figure them out by multiplying the probability assigned to each of these categories, the probability that you get this thing, times how many attempts are going to be made, in this case, 300. Okay, so for every one of these problems that you'll do when you're doing goodness of fit, they're going to give you the expected or the observed frequency. They'll always give us the observed frequency. We calculate the expected frequency. And then we're going to use this formula, which we've seen before, which basically says, are these close enough to where we think this is probably a fair die? Like this one's really close, right? We got 51. We're expected to get about a 50, so pretty close. Same thing here, 47 we're expected to be 50, around 50. Like I said, we know there's variation, right? The example I'll use again, if you flip a fair coin 100 times, nobody's going to be shocked if you don't get exactly 50 heads and 50 tails, right? Same idea here. Now here, this one's a little further out. Like, maybe there's something to this. Maybe this is not a fair die. Maybe a 4 is not likely to happen for some reason. So that's what we have to do. We have to figure out how far away each of these are, which is what we'll do right here from this formula from last time, observed minus expected, OE, right? We're going to take every observed minus the expected. and we're going to walk through this, but this is much easier. So this one, here's the key. We need to be able to do this. We need to be able to do this part by hand. Be able to do, I'll say by hand. Now I'm going to show you how to do this on the calculator, but the problem is not all the calculators can do it. You have to have newer software in the TI-84. The TI-83 won't do it, but some of the newer TI-84s will. But we have to do it by hand anyway, okay? So be able to do this one by hand. If you are doing a goodness of fit test, we have to do by hand. Test of independence, don't do that one by hand. Test of independence is 10.1. Do that one, put it in the matrix, let the calculator do the work. But in this case, we can go O minus E. It's a little tedious, but it's not going to be bad. We're not going to have huge data sets here. So O minus E, so I go 62 minus 50 squared over E, which is 50, right? I'm doing the summation one at a time. Just go this minus this squared divided by this plus this minus this squared divided by this plus this minus this squared divided by this, right? So we go right down the line here, just according to the formula, plus 45 minus 50 squared divided by 50. And again, remember that normally these 50s will not all be the same. So normally you won't even have this. This looks like, it's a little misleading. There's always a 50 down here. Most of the homework problems, these numbers are going to be different each time. Okay, so just kind of keep that in mind. 32 minus 50 squared over 50 plus 47 minus 50 squared over 50. And then finally plus 51 minus 50 squared over 50. And this one's actually kind of easy to add up because of the common denominator. But if you add all these up, you will get 672 over 50, or about 13.44. Okay, so on a test or a quiz, I'd expect you to just show this here. So show me you know what you're doing, and then you can just put the answer. We don't have to go through and do all this and show every step here. You can just let your calculator do all those calculations. And then we need this final answer. So this is our chi-square. Now remember one thing though, you have to be careful here. When I do this problem here and I go 45 minus 50, and put a little star here. Be careful with this part. If you go 45 minus 50 squared, this is what you have to be careful about. Just going to give you the wrong answer, because think about what we're doing. Aren't we always squaring something? And when you square a number, don't you always get a positive result? So for this here, 45 minus 50, it's negative 5. But if I put it like this, the calculator is going to do order of operations. It's going to square this first. It's going to square the 5. It doesn't even see the negative. So it's going to get 25, and then the negative is there, negative 25. So just be careful. We don't want to square the 5 and take the opposite. We want to square negative 5. So what you can do is, as you're doing this, just don't even pay attention to the negative. It's going to be squared anyway. So 45 minus 50, just put 5 squared, right? That way you don't have to add all the parentheses in or worry about negatives. So just be careful about that. And then we've got a little note here. This will not be important, but it's like before. We have to have a large sample. So in order to do that, E has to be greater than or equal to 5. That's the same as last time in 10.1. These expected frequencies each have to be at least 5, which will always happen for us. Okay, so we've got our chi-square, 13.44. We need to figure out our degrees of freedom for goodness of fit test. Well, degrees of freedom always seem to have this n-1 formula, and this is no exception. Degrees of freedom is k minus 1. In this case, we use a k, where k is the number of categories. So for us, we have a 6-sided die, so k is going to be 6 in our case, right? There's 6 outcomes. so k equals 6. So degrees of freedom equals 6 minus 1, which is 5 degrees of freedom. So goodness of fit tests have k minus 1 degrees of freedom. If you remember test of independence, they had row minus 1 times column minus 1, right? They were different. But we are not using that here. We just have k minus 1. Okay, so we've got 5 degrees of freedom. And then we can find the p-value. So, of course, there is a chi-square table you can use. If you like listening to 8-track cassettes, you might like using the table. So I'll just mention it. It's on page A25 in the appendix, page A25. And it's sort of like when you use a student's t-table. You can get an interval of values, but you can't get the precision that you can with the calculator. So we'll do on the TI-83-84 is same as before. You go to the distribution, right? So it's the same as before from 10.1. Chi-square CDF is right by normal CDF and TCDF and all that other stuff. So we would go the p-value is equal to the probability that chi-square is greater than or equal to 13.44. That is equal to chi-square CDF. If you remember, chi-square is always right-tailed, just like before. So we have our lower limit, our upper limit, which you can always use 100 here, right? You can always use that, then our degrees of freedom. So just to recall here, when we use chi-square CDF, we have our lower limit, upper limit, and 100 always works because a chi-square of 100 is just not going to happen. Our calculator wouldn't be able to tell what that even means. And then degrees of freedom. And if you punch this in your calculator, you should get 0.0196. So, you know, from this point on, it's pretty much like every other one of these we've done. So reject or fail to reject, well, we look at our p-value. It is 0.0196. Remember what p-value means. It means p stands for probability. So this is saying roughly 0.02, so roughly 2%. So p-value is the probability that we could get that outcome we got if the null hypothesis is true. So this is saying basically there's only a 2% chance those distributions match, right? There's only a 2% chance that that six-sided die we've got has the same distribution as a fair die. So we look at this, though. We look at our p-value. We compare it to alpha. Now, in this case, alpha was 0.01, right? So we look at our p-value. We look at alpha, and our p-value is greater than alpha. So what that means is that we fail to reject H0, right? Now, me personally, I wouldn't want to be playing any high-stakes games with that six-sided die, but the line in the sand initially was 1%. Remember what alpha means. Alpha of 0.01 means that we are going to stick with our null hypothesis unless our sample has a 1% chance or less of happening. Well, our sample had about a 2% chance, which is more than this, so we're not going to reject it. We're sticking with H0, right? 2% chance, not a very big one, but not small enough. We're only going to reject it if it's a 1% chance. So we failed to reject H0. We're going with H0. And then they're going to want us to give a conclusion. And that'll, of course, always be in the context of the application. So we can say this. We can say this the way that we've always said it in the past, or we can use the new wording in the book. Remember that in the conclusion we always mention the level of significance. This is a perfect example of that. Had this been 0.05, we would have rejected H0. So we have to, in the conclusion, mention the line in the sand we're using, because if it were a different one here, we would get a different conclusion. That's why I always start off right off the bat saying at the 1% level of significance, right? That tells us our line in the sand. So let's take a look at this one and talk about how we can say this. So we could say, how we have been in the past. We could say at the 1% level of significance, and we could say, if we use our old wording, we would say the sample data or the evidence do not suggest H1, right? Because we're going with H naught. We could say do not suggest that the distributions are different. We could say that it'd be just fine. I'm going to use the new wording, though, just so you'll see it here and you'll be used to it in the book. So the new wording that the author uses, which basically says the same as our old wording, but just a little bit different language. It says, at the 1% level of significance, the evidence, when they say evidence, they mean our sample, right? The evidence is insufficient to conclude. Remember in 10.1 I showed you how they would just add this word in. That's the only difference in the conclusion. So we're going to say the evidence is insufficient to conclude that. Now I'm going to say H1. The distributions are different. Okay, so just kind of breaking this thing into pieces. At the 1% level of significance, nothing new there. Now what we're going to do is we're going to say the distributions are different. That's H1, right? That's H1. And what we're going to say is the evidence is insufficient to conclude this. The evidence is insufficient to conclude that the distributions are different. Right, so I'm just going to add a little thing on here, so you don't have to do this, but in other words, we believe that the die is fair, right? Because this is saying the evidence is insufficient to conclude that the distributions are different. So we're sticking with a null hypothesis that the distributions are the same. In other words, that six-sided die that person rolled has the same distribution as a fair die. Right? Just because the numbers are different just doesn't mean they came from a different distribution. Right? If you take a fair die and roll it twice, you're not going to get, and roll it 300 times twice, you're not going to get the same distribution. But it came from the same distribution, right? They're just that there's always going to be variations. So hopefully this makes sense. It's similar to what we said before. The evidence is insufficient to conclude H1, right? Because we're not rejecting H naught. If we had rejected H naught, then we'd be going with H1. Then we could say that evidence is sufficient to conclude H1. Okay, so just be careful with the wording. Sometimes what happens on test is students will say fail to reject H naught, and then the wording will say reject H naught. You know what I mean? So we just have to be careful with the wording. Just read, after you write it, read it, and make sure it makes sense. And let's see. I'm going to go over number 9 in these sign problems. That's a good one to look at. But let me show you how to do this on the TI-84. Now, notice it doesn't say TI-83-84. It's only on the TI-84, and it's not even on all of them. It's just on some of them. But I'll just show you, and again, I need to emphasize this because sometimes students are still putting this like thing I say only for checking. they'll put that on the test. And then students say, well, why do you even say that? Here's why I say that. Because if I don't say that, students will do it that way and say, you didn't say we couldn't do it that way, right? So I have to point out these things because otherwise students will just do these things and not learn anything. So I point them out so you're aware of them and that we're both aware that these are not legitimate ways to do the problems in class, but it's good to check. So this one, only to check answers, right? Only to check answers. Mainly, one reason, well, not mainly, but one reason is because not everybody can do this, right? Only to check answers. So when you do the problems, you have to do them like we just did, in the last example. But we put the observed frequencies in list 1 and the expected frequencies in list 2. So observed, those are the ones that we had, and then expected are the ones that are basically 50 all the way through, right? So I'm just going to kind of walk through this. It's not really important that we even go over this, but I just want you to be aware of it. So you go, of course, to stat and then hit enter to get to edit. And in list 1, we put those observed values. List 2, we put the expected frequencies. So list 2 is really easy. It's just 50 all the way down. We have 6 of them, of course. And then in list 1, we put those numbers that we were given. Okay, so if you're actually doing this in list 1, we're going to have, 62, 45, 63, 32, 47, 51. And then in list 2, we're going to have 50 all the way down. Okay, so then what we do is you go to the stat button. So from stat, you go over to tests. And then here's where some of you will be very happy, some of you will be very sad. Under tests, you have to look a ways, but it's right next to our goodness of fit test. So some of you will see this it's next to our chi-square test from 10.1. So if you look where our chi-square test was, which we used in 10.1, if you look right below it, you may see or may not see chi-square GOF test. It's goodness of fit test. So there's a decent amount of calculators that don't have that on there. So if you do have this on there, you can hit enter. And then it's going to say observed list 1, expected list 2. And the only thing you really have to put in there is degrees of freedom 5. And then you can hit calculate, and it gives us all the numbers that we just had. And if you are actually doing that, you'll see it'll give you the chi-square. So when you do this, it gives you chi-square. It gets the same thing we had. Gives us our p-value. Gives us the degrees of freedom, which we just gave it. And then it has this thing called, looks like this, contributions. And that is basically, it gives us all of those individual chi-square pieces. So if you look back here at what we had, it is basically giving us all of these right here. All of these things. It gives these one at a time, just list out these little pieces. Okay, so that's how to do it on the calculator. Only to check, and a lot of calculators won't even do that. So for goodness of fit test, we have to find that chi-square by hand. And then one of the problems I wanted to tell you about, because this is kind of a realistic type of problem. This is number 9. And sometimes realistic problems are a little tricky to get started, so I want you to be able to see how to do this one. This is an assigned problem, so I don't want to spoil the fun, but I want to give you an idea so you know how to get started. So if you look at, you really have to kind of see this one on page 647, on number 9. They give us this region under the normal curve, and they give us this degrees Fahrenheit. And they kind of lay this out here. And what they're talking about is they have the average daily temperature in degrees Fahrenheit in July in this town in Colorado. And they know that the distribution of these temperatures has a mean of approximately 75 degrees Fahrenheit, and it's got a standard deviation of 8 degrees Fahrenheit. And they have data from a 20-year study, which gives 620 July days. And what they want to know is that they're wondering if the average daily July temperature follows a normal distribution. So what we have to do with number 9 is we have to calculate the expected numbers that we would expect to have here. So when you look at this information here, you're going to see this 2.35%. I'm just going to tell you, one of the columns has these numbers that, if you think about it, if we combine them, they'll be very familiar numbers. So these are basically, if you add up 34 and 34, you get 68%. So these are numbers below and above the mean for a normal distribution. So if you were to add up all of these four, then you would get 95%. If you add up all of these, then you get 99.7%. So I have this drawing over here, sort of shows this. Now, looking at the percentage, you see my drawing is definitely a little off. It should cut down sharper. But basically, we're going to look and see if these temperatures in July, if they line up this way, so that we're thinking that the mean is 75 degrees. So we're looking at those 620 numbers and saying, are 34% of them in here, within 1 standard deviation of the mean? And there's 13.5 of them here. So we're going to look at all those 620 numbers, and if we were to standardize all the numbers, would they line up like this? In other words, would they follow this bell-shaped curve? So that's what we're looking at. So if you look at the observed number of days, they've got like 16, 78, 212, and so forth. What we want to figure out is, well, 2.35%. What's 2.35% of 620? And what's 13.5% of 620? What's 34%? So should we, if we figure that out and line up those numbers, do they agree with this? So to find the expected value, I'm going to make a little category here, the expected value. What we do is we take 620 and multiply it by each one of these, but as a decimal. So if we take 0.0235 times 620, we get 14.57. So we get 14.57 days. That's our expected number of days. And if you look at the observed, they tell us we had 16 there. And then the next one, 13.5% of 620. So we go 0.135 times 620, and we get 83.7. So there were 83.7 days here. And this corresponds to temperature readings, which you can look when you look at the problem, you'll see exactly what it's talking about. But all of them based on following this bell-shaped curve. Now the observed days in this category, there were actually 78 observed days. So you just kind of keep going. You figure out your expected values by multiplying each of these as a decimal times 620. And then you compare them to the observed values, and then you do the same, pretty much the same thing we did in the last problem. And then you see, do the test and see if it seems that these distributions are the same or not. So that'll get you started in number 9. But basically, every single one of these problems, we are going to need to find the expected number, and we'll have the observed number. Then we run it through the chi-square test. So give it a try, and of course, let me know if you have any questions.